morning, ladies and gentlemen. My name is Artur Gańcza, and together with Maciej Niedźwiecki, I'm the author of an article for Eusipco 2021 conference describing regularized identification of time-varying FIR systems based on generalized cross-validation. Let me start by defining the problem that we solve in our paper. We consider a non-stationary system that can be described by the following equation. Theta denotes the vector of time-varying unknown parameters. Phi is a regression vector made up of previous values of the known input signal, and E is a white measurement noise. Our goal is, of course, to find those parameter trajectories having U and Y. We assume here that we don't have any prior knowledge about the way system parameters vary with time. The exemplary parameter changes that we use in our work are depicted in this figure. Derivation of our method requires the assumption that inside some analysis window, parameter changes can be described as a linear combination of some known functions of time. Under this assumption, we transform our original time-varying model into a higher order, but time-invariant one. Of course, this description is assumed to be valid only inside the analysis window. Then we use the least squares technique to obtain some estimates of the coefficients alpha, which are further used to obtain the estimates of the original system parameters at the time instant corresponding to the center of our analysis window. Then the window is shifted by one sampling interval to the next position, and the estimation is repeated. This pointwise procedure we call the local basis function method, LBF, and this approach provides high-quality estimates of model parameters, but since the number of estimated hyperparameters alpha can be quite high, it also requires higher computational costs and longer analysis window to guarantee good conditioning of the regression matrix. Both of these drawbacks can be overcome if we use a technique approximating the behavior of the LBF approach. This method consists of two steps. First, we obtain pre-estimates that are unbiased regardless of the type and speed of parameter changes. However, unbiasedness comes at the cost of a high variance of pre-estimates. This is why they cannot be used as a final product. To solve the large variability, we propose a second post-filtration step. Please note that in order to obtain pre-estimates, one should know the true covariance matrix of the regression vector. In the next slides, we will see how to overcome this problem. But first, we can compare results yielded by the exact LBF method and the approximate method that we call fast local basis function, FLBF method. Here, red lines show the true parameter trajectories, while the black lines are the estimated trajectories. As you can see, the FLBF approach can provide estimates of comparable quality at a substantially lower computational cost. So how exactly are the pre-estimates computed? It turns out that the whole expression for the pre-estimates can be approximated by the result of inverse filtering of the exponentially weighted least squares estimates of system parameters. Pre-estimates obtained in such a way can be seen as true parameter trajectories contaminated with white noise with a large variance. Therefore, we again use the assumption that inside some analysis window, parameter trajectories can be described as a linear combination of known functions of time. And we again apply the least squares procedure to find estimates of alpha. This scheme is in fact equivalent to the Savitsky-Golay filtration, and it turns out that if the basis functions are the same as in the LBF method, the FLBF approach can be used as an approximation of LBF. In this article, we propose a further improvement of the FLBF procedure by applying a carefully designed regularization. It is well known that regularization can reduce the mean squared estimation errors by improving the bias variance trade-off. And please note that in our setup, we are not interested in direct regularization of hyperparameters alpha. Instead, we apply ridge regression to the vector of variables representing model parameters. The formulation of the problem is as follows. And it can be shown that the regularized estimates can be obtained quickly by a simple rescaling of the FLBF estimates. To find the proper value of the regularization constant, we use the generalized cross-validation criterion. And we note that in our case, it can be directly optimized. The explicit formula is very simple and depends on the estimate of noise variance and FLBF estimates. Since we require the regularization constant to be positive, we use the following rule to obtain optimal regularization constant. And the practical implementation of this rule is shown here. Please note that there is a meaningful interpretation of this rule, namely, when the FLBF estimate of a system parameter falls below some noise-dependent threshold, we disregard this value as unreliable and replace it with 0 instead of shrinking. The presented algorithm was tested using computer simulations. We started by generating impulse responses of the three systems shown here. Then we truncated those impulse responses and generated parameter trajectories by morphing the A impulse response into B and then B into C. For morphing, the Hahn window was used. Then we prepared a Gaussian input and generated the output signal using the simulated time-varying FIR model. Here we present our setup. Please note that the applied simulation scenario goes beyond our initial assumption, since the simulated parameter trajectories cannot be expressed as a sum of the finite number of the adapted Legendre basis functions. We compare the FLBF algorithm with its regularized version using 4 different signal-to-noise ratios and 2 different speeds of parameter changes. For the fast parameter variations, the total time span for a transition from impulse response A to C was equal to 1000 observations, while for slow changes, this interval was twice as long. The results obtained for a different number of basis functions are collected in the tables. All of these results were obtained by combined time and ensemble averaging. On the left, we can see the true impulse responses of systems A, B, and C, depicted by black lines, and superimpose on them the FRLBF estimates obtained for SNR equal to 20 dB. It is easy to see that the greatest improvement is obtained for the lowest SNR values and the highest number of basis functions. It may also happen that when the FLBF estimates are already of a very high quality, the proposed FRLBF scheme can slightly deteriorate the results, but still will produce very accurate estimates. So to summarize, the problem of identification of a non-stationary stochastic system was considered and solved using the time-localized variant of the regularized basis function approach. The generalized cross-validation criterion proves to be an effective tool for choosing regularization constant, and the regularized FLBF method provides results that are either better or only slightly worse than those yielded by the FLBF estimator. Thank you for your attention.